Hi, this is Saurabh Agarwal from Truechip, and a very good afternoon to everybody here who has joined from India, Southeast Asia, and a good morning to the people who have joined from Europe. I welcome you to this webinar of DDR Exploring DIMMs, and today we will be covering the following: the DDR overview, followed by exploring various types of DIMMs. Then we will take up the basic architectural insights, followed by the different schemes used to configure DIMMs, the future roadmap, and we will take up the Q&A at the end. There's a blue question mark box on your screen, ladies and gentlemen, so you can just click on that question mark and can type in your questions. We will take up all the questions at the end of this webinar. So over to my technical team now. Enjoy this. Thank you.
Good afternoon, everyone. Let's start with a brief overview of DDR. DDR stands for double data rate. It's a memory technology based on synchronous dynamic random access memory, also known as SDRAM. DDR SDRAM access is twice as fast of SDRAM because DDR data transfers occur on both the edges of the clock signals as compared to the SDRAM, in which the data transfer occurs only on the rising edge of the clock. There was another side benefit to this change as well. It meant memory could run at a faster, at a lower clock rate using lesser energy and achieve the faster speed. Some of the key features of DDR are: it strikes a good balance between transfer rate, cost, and power consumption. It has high performance as it is faster and more efficient. It supports ECC, that is, error correcting codes, and CRC to detect and correct the errors. It is used to maintain the reliability of the memory. It also supports automatic self-refresh operation, which depends on the operating temperature. It is an ideal solution for numerous applications ranging from high-performance computing and the supercomputer to smaller power-constrained mobile devices. Throwing some light on the evolution of DDR. As technology progressed and processors became still more powerful and demanding, DDR alone became insufficient. It was followed in 2004 by DDR2 with an internal clock running at half the speed of the data bus, that is 800 mega transfer per second. This meant it was twice as fast as original DDR using lesser power of 1.8 volts. DDR3 was next out of the gate, which debuted in 2007, with its internal clock cut in half again. Its speed about twice, that is 2133 mega transfer per second, that of DDR2, and power usage reduced even more over its predecessor. The DDR4 came into existence in 2014, which has transfer rate up to 3200 mega transfers with the voltage of 1.2 volts. The evolution of DDR has exponential growth with applications requiring more memory, so the bandwidth increased multiple fold from DDR to DDR4 from 1 GB to 16 GB. In 2018, the latest version of DDR, that is DDR5, is expected to be launched. Talking about the DIMMs, a DIMM, that is dual inline memory module, is a double SIM, that is single inline memory module. Like SIM, a DIMM is a module that contains one or several random access memory chips based on a small circuit board that connect it to the computer motherboard. A SIM has typically 32 data bit path to the computer that requires 72 pin connector. For DDR SDRAM chips, which have a 64 data bit path connection to the computer, SIMs must be installed in inline pairs since each SIM can operate on 32-bit path. DIMMs eliminated this practice of pairing two SIMs as one. A single DIMM can be used instead. As faster dynamic random access memory grew, DIMM circuits also evolved. Another evolution in the DIMMs were in the use of cooling fans, which help vent the heat into the computer enclosure and away from the motherboard and the CPU. The point to be noted is that DIMMs are not backward compatible to SIMMs. And DIMMs is not limited to PCs only. It is applied to a variety of electronics products that includes printers, notebooks, and also the networking hardware. DIMMs are available in many forms. Some of the DIMMs are as follows: UDIMM, that is unbuffered dual inline memory module; SO-DIMM, small outline dual inline memory module; Micro-DIMM, micro dual inline memory module; RDIMM, registered dual inline memory module; FBDIMM, fully buffered dual inline memory module; and finally the LRDIMM, that is load reduced dual inline memory module. Let's see the differentiating features between the DIMMs. UDIMM is a type of memory chip used mostly in computers, laptops, and mobile systems. It runs faster than registered DIMMs and cost less, but they're not quite stable as RDIMMs. In UDIMMs, each chip of the memory module is addressed individually and in parallel by the memory controller inside the CPU. The memory chips in use today are a type of UDIMM. In UDIMM, there is no buffering present on the address and data path between the memory controller and the DRAM. The memory controller sends all the commands directly to the DRAM. Then comes the SO-DIMM and the Micro-DIMMs. Space is at premium in notebook and small form factor desktop computers, making it difficult to find room for full-sized memory modules. As a result, these computers use memory modules with smaller circuit boards. SO-DIMM make it possible for a smaller computer to have the memory capacity comparable to the full-size computers. One can identify the SO-DIMMs primarily by their size. A standard DIMM is slightly over 5 inches long and SO-DIMM is slightly over 2.5 inches long. That is the small space. With the more functionality included in the next generation notebooks, the less space remain for DRAM itself. Therefore, need for DIMMs with smaller form factors and small densities or the same densities as SO-DIMMs arose, which are predominantly used in the notebooks. Hence, the Micro-DIMM came into the picture. The Micro-DIMM is a memory module with nearly 50% higher bit density and which requires 35% less board space than the SO-DIMM at the same memory density. With the Micro-DIMMs, even more applications like ultra-mobile PCs and extremely slim and compact notebooks designs are also enabled. Basically, SO-DIMM and Micro-DIMM are the unbuffered DIMMs, that is UDIMMs, which require smaller area and the capacity. SO-DIMM and Micro-DIMM were followed by the FBDIMMs. Fully buffered DIMMs are used in servers to increase the reliability and to access more memory with a system. Fully buffered DIMMs have an AMB. AMB stands for Advanced Memory Buffers. The controller sends all the memory requests through AMB. Unlike other buffers, this has a serial interface to the memory controller, which allows greater data width without having to increase the number of pins on the memory controller. Ideally, this approach reduces the physical number of signals at the input of DIMM and therefore unclutter the physical wiring with increasing the number of memory modules per system. This method is only used in DDR2. Now it has been outdated. RDIMMs. Registered DIMMs is dual inline memory module with improved reliability. The RDIMMs uses a hardware known as registered clock driver registers that buffers the control signals and not the application data to the memory module. This buffering adds the clock signals and uses more power but handles the heavier electrical loads placed on high speed, high density module better than the old DIMMs. The extra clock cycle effect is overshadowed by this buffering as it reduces the load on memory controller because it points to the dedicated registers rather than accessing the DRAM directly. This improved stability and scalability comes at a higher price. That's why RDIMMs are mostly found in servers and not in the desktop computers or the laptops. LRDIMMs or load-reduced DIMMs are a new type of industry standard modules for servers. They are similar to register DIMMs, which are built on a memory module printed circuit board and uses the same type of DRAM chips. This is where the similarities end, as LRDIMMs function differently from the register DIMMs. LRDIMMs add a special memory buffer to the bus affixed to each memory module. In RDIMM, the memory bus functions in parallel mode and all DRAMs are controlled by the memory controller. As more and more DRAMs are built into the RDIMM, the electrical loading of the memory modules increases, which results in memory speed drops. LRDIMMs can navigate outside of these restrictions through the use of memory buffers. All command and control signals are transmitted to the RCD, which further transmitted to the memory buffers. And now the duty of the memory buffer is to handle all the read and write to the DRAM chips. Talking about the architectural insights, the DIMM architecture provides two unique features, namely address mirroring and the output inversion. When routing connections are done, it requires a lot of vias, conductor corners, long traces, etc. It doesn't matter how you physically route your RAM array. What matters is that the data written to a specific locations must be read from that same location, not the another one. Thus, generally, you can connect address and data pins group of a single or a multiple RAM chips in any way which you see the best. For routing to have the shortest tracks and minimal number of vias. The command and address bus pins on the DRAM are defined in a manner that allows for these short trace lengths. This allows the most flexibility with these pins. Even ranked RAM pins are wide straight with no mismatch between the connector pin assignment and the DRAM pin assignment. Some of the odd rank DRAM pins are cross-wired accordingly, whether they have some special function. Address mirroring allows for easier routing by flipping specific pair of address bits on the odd ranks. Memory controller has to switch the address bits in an MRS command to accommodate address mirroring for correctly configuring the DRAMs. Output inversion. In RDIMMs and LRDIMMs, the output inversion is enabled inside the RCD, that is register clock driver, by default. It is done to conserve power. In order to ensure that the DRAMs receive the correct uninverted MRS bits, the host to register to DRAM MRS programming is done in two steps. The first step is the A side DRAMs are programmed using non-inverted addresses from the host. Then B side DRAMs are programmed using inverted addresses for the invertible signals and non-inverted addresses for the non-invertible address signals from the host. Configuration schemes.
So ladies and gentlemen, there is a blue question marks box on your screen. You can just type in your questions there and we will take up all the questions at the end of the webinar. Thank you.
Proceeding on to the configuration schemes. The table below shows the different configuring methods for RDIMM and the LRDIMM. The first one is configuring RCD, that is register clock driver, using register control word, that is RCW. There are two methods to configure RCD. The first method is the memory controller configures internal register of RCD known as register control word by sending mod register 7 command. For reads, the RCW command is sent by the controller to the RCD to move the specific register configuration into a special multi-purpose register in the DRAM. Then the data of the MPR is read out onto the controller. The second method is through inter-integrated circuit, also known as I2C. There is a SPD or serial presence detect module on the DIMMs. The entire configuration is set into the SPD module. Through I2C, the configuration is sent from SPD to the RCD. The memory controller sends all the commands to the RCD, which further sends to the DRAM. Now configuring data buffers using the buffer control word. The memory controller configures the DBs, that is data buffers, through RCD. RCD configures the internal register of the data buffer using the buffer control word. In this also, mod register 7 is used to configure the DBs. When 12th bit of the mod register 7 is 1, it is used for configuring data buffers. Whereas if this bit is 0, it is used for configuring the RCDs. The memory controller can read out the DB buffers configuration by sending buffer control word command through the RCD to read out from the multipurpose register of the data buffer. I2C configures the data buffer through the RCD itself. Now proceeding on to the configuring DRAMs using the MRS. Memory controller sends all the configuration of DRAM to the RCD through mod register commands, that is with the help of MRS0 to MRS6. RCD sends all the configuration further to the DRAM. The configuration set in the DRAM can be read out through multipurpose register, that is with the help of ampere read command. The point to be noted is both the DRAM and RCD support even parity. Let's see the future roadmap of the DIMMs. Non-volatile dual-line memory modules, that is NVDIMMs, are a new brand and very different storage technology. NVDIMM replaces a traditional memory sticks in a server and allows the data to remain in place when the power is removed from the system. This is achieved by adding flash to the DRAM on the DIMM. When power goes off, either deliberately or by a failure, the data from the DRAM is copied into a NAND flash memory. This allows the data to be instantly available without reloading from the device when the power is restored. There are two distinct NVDIMM models available. Both promises the huge performance benefits and are poised to impact everything from data centers to the smartphones. One type of NVDIMM is NVDIMM-N. NVDIMM-N uses a high capacity, about 16 GB per DIMM, and matches with an equal amount of flash. This DIMM is as fast as data transfers at DRAM because it speeds back and forth. It is suited for a use where the speed of the access to persistent data is very important, but it is limited to around a terabyte. The other type of model is NVDIMM-F. NVDIMM-F uses a small capacity DRAM as a buffer to a very large flash. This DRAM bus is used to read and write into a large flash memory as much as several terabytes per DIMM pair. The differences between the NVDIMM-F and N is NVDIMM-F is slower than NVDIMM-N. Application of non-volatile DIMM card is it may be used to extend the system memory or supply high performance storage. By the end of 2018, another type of DIMM, that is NVDIMM-P, is to be launched. Truechip DDR VIP model. To verify a DDR design, Truechip provides an environment which includes, from the left hand side, the compliance test suite, the controller, followed by the DFI PHY, and finally the DRAM model. To communicate between the controller and the PHY, there is a DFI interface, and for the communication between the PHY and the DRAM model, there is a memory interface. On both the interface, there is a monitor and a scoreboard. The monitor helps in checking the violation of the timing parameters, and the scoreboard helps to check the data integrity. DFI scoreboards collect the data from the DFI interface and also from the memory interface, which further compares the data for read and write transaction. Similarly for the DDR4 scoreboard, which collects the data from the memory interface and further checks the data integrity for the read and write transaction from the memory and to the memory. For the Truechip model, configuration of the PHY is quite easy. The Truechip model is easy plug and play. It can be easily integrable and can be used to verify the duties, either its controller, either its PHY, or either it's the DRAM. It is used to verify all the duties. The differentiating features of the Truechip DDR VIP are: to depict the real hardware, clock skews into the memory module are configurable, as different chips get the clock at the different times. Therefore, each module will undergo trainings for correct sampling of the data and will perform their operations. It also provides weightage-based randomization on the address signals. There is an option to skip the initialization process in order to save the time. All the individual components of the VIP are independent. One can use the passive monitor and scoreboard as well if all the components are of the user. Truechip provides the integrated model in which DDR is integrated with the AXI for write and read transaction and AHB and APB for the further configurations. This helps us to depict the SOC model and verify the controller as a DUT. Truechip model also provides the graphical user interface for easy debugging. The diagram shows the integrated environment. In the integrated environment, DDR VIP model has been integrated with AXI, AHB, and APB VIP models. This model depicts this real SOC model. There are two methods available in the integrated environment. First one is the direct method. The second one is the sequence converter method. In the direct method, sequences are written directly for the AXI, AHB, and APB masters. When running without a DUT, a DDR4 converter in the DDR VIP is used to convert AXI, APB, and AHB bus to internal Truechip DDR controller protocol format. In this method, sequences are made with the help of user-friendly macros. In the other method, that is the sequence converter method, a protocol converter on the left-hand side of the diagram shown in the blue color is used, which converts AXI, APB, and AHB bus to a Truechip internal DDR protocol format. DDR sequences are converted and output is sent to AXI or AHB or APB masters, BFM. Talking about the GUI model, the Truechip VIP comes with inbuilt graphical user interface to enable easy debugging for the users. On the screen, you can see the sample transaction for read and write. The first column signifies the time when the write transaction was encountered, followed by the row and column addresses onto which the write has to be carried out. The last column of the transaction block shows the data that has to be written into the memory. Apart from this, on the right hand side, we have a transaction details block which explains whether OTF, that is on the fly mode, was enabled, which band group was accessed, is the auto precharge need to be done. It also signifies the burst length and the MRS command. It shows the MRS register addresses. Moving further, if an error occurs, it will be highlighted in the red color. But in the current diagram, the transaction details is of the right transaction, which is shown in the gray color. You can get all the details of the error by selecting on the red color row. Once you select it, the right hand side transaction column will show the error ID along with the actual and the expected value, so that user can get the timestamp where the error actual and expected data if the data of the MRS is mismatch occurs. By placing the cursor on error ID, you can get the details of the error as you can see from the current figure. The description of the error is highlighted in the black color row. Now we are open for question and answer.
Okay, thank you. We have done a good deal of webinar here. Now is the time to move on to the Q&A. So we have a lot of questions which are coming up, and I'm just taking up the first question, which is by Chetan L. And in slide 13, could you please give more info on the side A and side B addressing of DRAMs? In slide 13, could you please give more info on the side A and side B addressing of DRAMs? So can you just put up as an answer question by Mr. Chetan?
Hi Chetan, thank you for the question. Okay, so the RCD divides the DRAM into two sides, that is A side and a B side. A side receives the non-inverted signals, whereas B side receives the inverted signals on the pins that do not have a special functions. A and B side can be disabled to the RCD. I hope I have answered your question.
Okay, so there is another question which is which is from Divya Jha. So I will display the question. So she's asking, why was FBDIMM not continued after DDR2? Why was FBDIMM not continued after DDR2 by Divya Jha?
Hi Divya. That's a nice question that like everyone is confused why the FDIMM was not able to continue after the DDR2 and it's outdated as well. In fact, we know that FDIMM uses the AMB, that is advanced memory buffers. But the problem with the FDIMM is that like the first one is the input frequency had to be 4 folds higher than the memory clock frequency, which further takes it into the microwave frequency. And getting into the microwave frequency range, it had to lead to the many technical difficulties. Because of this, it's unsuitable for us to continue further on DDR3 or DDR4. That's why we are not using FBDIMM further.
Okay, so next question we have actually I will say 2 questions which are coming from Mr. Hira Lal Bhadrecha. So he's asking, can I mix different DRAM memory speeds? Can I mix different DRAM memory speeds? And the same another question that he is also asking is, what is NVDIMM-P? So can we answer both the questions?
Okay.
Yeah.
Okay. Hi, Mr. Hira. So like answering your first question, mixing the different memory speeds. No, you can't mix the different speeds like of the DRAM because cache latency and other timing parameters are there. Which depends on the different speed grades. But you can use the frequency between the min and max limit of that speed grade. You can't mix it, but you can use the min and max of that thing. And your another question shows the what is NVDIMM-P? Okay, so as explained by me that there are 2 NVDIMM models available right now. That is NVDIMM-P. NVDIMM-N and NVDIMM-F. So there is so much problems in the NVDIMM-F as it uses a lot of flash memory rather than using the your DRAM models. And also the NVDIMM-F is also slow as compared to NVDIMM-N. So we are proceeding on to the NVDIMM-P, which will be using the basis of the NVDIMM-F, but they'll be proceeding on to the NVDIMM P itself with the same speed as that of NVDIMM-N. That's why they are proceeding on to do NVDIMM-P.
Yeah, hope we have answered both of your questions, Hira. Moving on to the next question, and this question is okay. This question is by Adil Nazir, and he's asking, why was SPD block introduced into DIMMs? I repeat, why was SPD block introduced in DIMMs?
Okay. SPD is like a special serial presence detect module, and for a computer system to recognize a memory module, the module needs to have a chip onto it that communicates with the specification of the module itself. And if you plug in the different memory chip module, that will be a failure, that it will not be able to communicate with that. So SPD module contains all the details of the configurations your memory module support, so that there is a best communication between the controller and the DRAM. That's why there is a need for introduction of SPD block.
Okay, so we have another question now. This is coming from Prakash Kedia. Prakash Kedia is asking, how can my memory controller be verified using your integrated environment? Again, I will just rephrase the question. So he's asking actually how the Truechip VIP integrated environment can be used in his memory controller, right?
Okay. As explained by me that there is a integrated environment. Integrated environment includes AXI, AHB, and APB. And like earlier, the need of integrated environment is that you must be having an interface before the controller that communicates with the controller, so that it can check the transactions that are going into and out of the controller. So for that, we have two monitors. First one is for the AXI monitor that will check all the write and read that are going into and out of the controller. On the other hand, for the configurations things, we are using like our AHB or APB monitors. So with the help of these two monitors, and also we have a scoreboard as well, with the help of these things, we are able to like verify the memory controllers.
Okay, I think there is a very interesting question which I can see right now on the screen. It's by Sanjay Kannan from Chennai, and his question is, what can the prime advantage of using unbuffered DDR versus registered DDR RAM model? What are the prime advantages of using unbuffered DDR versus registered DDR RAM model?
Okay. The major advantage that I see for the UDIMMs, that is unbuffered DIMMs, over the registered DIMM is that registered like unbuffered DIMMs are faster than RDIMMs. But when the large memory is required, its performance goes down. And moreover, like RDIMMs are more stable as compared to the UDIMMs. So I hope I have answered you the query.
Okay, I have many more questions which are popping up, but I'm so sorry that I cannot take up all the questions, but I will take up the one last question. It's from Jonathan Palais, and okay, so he's asking, as you mentioned above, about weight age-based randomization. Can you please tell how will it be useful? So we have mentioned about weight age-based randomization. So he's asking as in how will it be useful, by Jonathan Palais.
Okay, hi Jonathan. Okay, so the utility that we are providing for the weightage-based randomization is only on the address signals. And if we are going with the address signals, the problem is that we are not able to check the complete density of the model. So we are dividing the memory model into the many parts, like 6 parts, or let's call it a blocks, 5 blocks, 6 blocks, 7 blocks. And then the utility of the blocks is that we can write the particular thing that we want to write in that, and we are checking that our memory is working or correctly or not. For that purpose, we are randomizing the address, and that is also a weightage-based randomization.
Okay, thank you all, ladies and gentlemen, for joining in today for this webinar, and I'm very thankful to you for that you have taken your time from your busy schedules, and please keep tuned in for the next webinar, which will be on USB. Till then, take care. Goodbye. Have a nice day. Thank you.